Okay, let's have our second attempt at proving 3.8. This time with my machine on mains pair. And of course I realised that I wasn't on mains pair when I saw that little blip in my underline there. Okay, so the proof of 3.8. So we've got our m-dimensional vector space, so we're using notation as above. So E is m-dimensional over F, and V1, I don't think I should underline them, it wouldn't be appropriate at this stage. V1, V2 up to Vm is a basis of E and this basis will be fixed for the rest of the proof. And I'll assume that m is at least 1 to avoid any trivialities. If it's a zero-dimensional space, it's not going to be interesting. Otherwise, it's trivial. So the first thing we do is, as above, you've got this isomorphism T from F to the n goes to E. T from F to the n goes to E, where T of your n-tuple, your m-tuple, is the sum from k equals 1 to m of lambda k vk. It takes your vector of scalars and makes an appropriate linear combination of your basis out of it, and that gives you a linear isomorphism from f to the m, not f to the n, to E. We now use that to transfer the norm across, and we'll use Euclidean norm. So we give f to the m Euclidean norm, norm 2, so norm of lambda 1 up to lambda m 2 is the sum of the squares of the modulus. Remember, they might be complex numbers, so we don't just square them, we square the modulus just to be safe. And then you square root it at the end. Then using T or T inverse, whichever you like, we transfer this norm across. So using T to the minus 1, whatever, we transfer the norm across over to E to define what I'll call norm 2 again. This isn't the same norm 2, of course. I'll just call this norm 2. You want to call it, give it any other notation you like. You can give it another notation if you like, but I think of this as a 2 norm defined on E. And so, of course, the norm of sum from k equals 1 to m of a lambda k vk, the norm of that combination, and I guess I don't need the brackets, the norm of a particular combination like that, of course, we know every element of E is uniquely written in that form, so it makes sense to define this, and I'm calling it the 2 norm, is, again, the sum from k equals 1 to m of mod lambda k squared to the half. So I'm thinking of that as the equivalent, essentially a Euclidean norm, but put on this abstract vector space that doesn't have to have anything to do with the concrete vector space f to the m that you started with. It's just isomorphic to it. But of course, by using this, with E with norm 2 is then isometric to f to the m with norm 2. Remember, they're different norm 2s, but you can see the relationship. And what do you get from that for free? If you put this particular norm on E, E is complete, because we know that f to the m with norm 2 is complete. And we know that Heine-Borel theorem is true here, so it's going to be true in this isometric metric space here. Heine-Borel theorem will be true, Boltzmann-Weierstrass will be true, everything like that. So then, from properties of f to the m with norm 2, we know that, let's see, what do we get for free? We get that E with norm 2 is complete. So that's a Banach space. And the Heine-Borel theorem, the Heine-Borel theorem is valid in E with norm 2. So subsets are sequentially compact if and only if they're closed and bounded. So it's norm 2 sequentially compact if and only if it's norm 2 closed and bounded. Because, of course, we're going to put some other norms on E in a minute. And Boltzmann-Weierstrass is also true. We won't need that one, but I'll mention it again. Boltzmann-Weierstrass. Is everybody happy that I've fixed some basis and that I've defined a particular norm in terms of that basis on this vector space so far? Are people happy with that? And I've told you some properties that you would get from putting this particular norm on. Now, our challenge is to prove that every other norm on E is equivalent to norm 2. So that's what we're going to prove. So now, let's norm be any norm on E. I don't care. And our task is to prove that it's equivalent to norm 2.
By the way,
Yes?
can M be infinity?
M?
Point.
No. M is this is a finite dimensional vector space. This is, we're proving 3.8. And so we talk about a finite dimensional vector space.
Okay.
So it's a natural number here. I eliminated 0 because that's a boring special case. So we'll prove that norm is equivalent to norm 2. On E. We'll do this by finding constants both ways round. And one way round, you get a constant for free. So notice, throughout this proof, M is fixed, and the vectors, the V vectors are fixed, and so on. So let's get a really crude estimate one way round. So first, we obtain a crude estimate, but it doesn't matter how crude it is, of the form norm x less than or equal to some constant times norm x2 for x in E. Let's see how you do that. Remember, we're fixing M here, and we're fixing V when up to Vm. So our constant is allowed to depend on those. C will be in terms of M, V1 up to Vm, but that doesn't matter. Because you're allowed to do that and say, we picked out our base at the beginning, so our constant's allowed to depend on those. Let's see how you do it. Well, let x be in E, then say, well, x is equal to lambda 1 x1 v1 plus and so on plus lambda m vm for some scalars, unique scalars, lambda 1 to lambda m. We have norm x2, we know, as a sum from k equals 1 to m of mod lambda k squared to the half. But what about just norm x? We don't know much about that. Without using the 2, what about the ordinary norm of x? That's the norm of sum from k equals 1 up to m of lambda k vk. Now I would want a really crude estimate for that. You can choose how subtle you want your estimate to be, but crude will do. That's less than or equal to the sum of the norms just by the triangle law. So that's smaller or equal to sum from k equals 1 to m of, well, the norm of lambda k vk. That's by the triangle law. That's equal to, of course, the sum from k equals 1 to m of modulus of lambda k times the norm of vk. So far, so good. My constant will, of course, depend on the norm I happen to be looking at the moment as well, which is also okay. If I take a different norm, it may well be I need a different constant. So let's have a look. What do we get here? Any suggestions for what one could do next? There's a really crude approach and there's a more subtle approach. So any ideas? I want to express this somehow as less equal to some constant times the 2 norm, the Euclidean norm of the vector with just the lambdas in. Okay, you could take the supreme of the norms of VK of the norm VKs out, and then you'd have the sum of the moduli in here, which would be perhaps a bit bigger than the 2 norm, and but no more than m times bigger, and so you could do that. So this is easily smaller or equal to m times max over 1 small equal to k small equal to m of the norm of the VKs times the norm x2. For example, that's one way to do it. Or more subtly, so this is very crude. It's good enough though. That would do for C. Or, if you want to be a little bit more subtle, you can use Cauchy-Schwarz instead. Is there a C in Cauchy-Schwarz? I never remember. Okay. But not in Schwarz's lever? I think there's one with a C and one without at least. The sum from k equals 1 to m of mod lambda k norm vk is actually less than or equal to, by Cauchy-Schwarz, sum from k equals 1 to m of mod lambda k squared to the half times the same thing with the norm vk's. So less crude is you could take C to be this. But I don't care which of them you use. Okay? All we want is that you get a constant, and that in this case, but the conclusion is, so we have shown either way that norm x is less than or equal to some constant times norm x2 for all x in E, and norm, and that constant C depended on m, v went up to vm, and the norm we were working with here. But you've got that it's less equal to some constant times the 2 norm. Now we want to get the estimate the other way around. And this is the weird bit. We use this estimate to help prove the estimate the other way around, which is very odd. I always think that's a very strange thing, but it's a typical functional analysis proof that somehow information is like having information about continuity in one direction, giving you automatically information about continuity in the other direction when you don't expect it. So I think that this is an amazing trick, using compactness and using what we know about norm 2 to deduce that everything really nice happens about norm. I'm going to do a proof by contradiction. So I want to claim, to finish, that there exists another constant, C2, such that norm x2 is less than or equal to C2 times norm x
for all x in E.
The result is then, if once we've done that, we've finished. Okay, that's what we're trying to establish. So we'll prove it by contradiction. Suppose for contradiction no such constant C2 exists. And of course it's greater than 0 exists. I'll put a greater than 0 in here. Suppose there's no such positive real constant, and we do not allow infinity. Then, as usual, what did we do last time? We're going to do something with a sequence. So what do we have to do? Just like in last lecture. If there's no such constant C2, what can we do? That's right. So we know that then we can find a sequence xn exhibiting the failure of n as a possible C2. Okay? So we can choose a sequence xn contained in E such that norm xn2 is greater than n norm x for all n in the natural numbers. N norm xn, exactly. Thank you. Why not? Why shouldn't that happen? Well, what we're going to do is normalize just like last time to get an element, a sequence of elements in the unit sphere with respect to norm 2. And the nice thing about the unit sphere with respect to norm 2 is that it's compact. We will then take a convergent subsequence and discover that we have a sequence that converges to something that's non-zero and to something which is 0. Let's see how that works. So, just like last time, this is a very familiar trick. You set yn equals 1 over norm xn times xn in E. Now, why is that safe? Why am I not dividing by 0? Because, of course, just like last time, that strict inequality shows that xn is not 0. So let me note, for safety, xn is not the 0 vector here. Then let's have a look. That should be norm xn2 I want to divide by, because I want it to be normalized with respect to norm 2, not with respect to norm. So two things happen, just like in last lecture. We've got norm yn2 is equal to 1 for all n, and norm yn without the 2 is less than 1 over n. So yn tends to 0 with respect to norm 2. Norm. But all of the norm yn2s are 1. So we've got a choice now. We can use Boltzmann-Weierstrass, or we can use Heine-Borel, whichever you like. But we know that because of the properties of norm 2, which is just a Euclidean norm, we've got Boltzmann-Weierstrass valid for norm 2, or Heine-Borel valid for norm 2, and we can say that this has got a convergent subsequence. Why didn't I do it Boltzmann-Weierstrass? I normally use Heine-Borel. I'm going to use Boltzmann-Weierstrass this year. By Boltzmann-Weierstrass, for norm 2, which we already know. Yn has some norm 2 convergent subsequence. Which I'll call Zn. Perhaps I should put brackets around. The sequence Yn has some norm 2 convergent subsequence, which I'll call Zn. Though if you want to call it Y sub n sub k, you can. I don't care. Your favourite notation for subsequences is allowed. Since where I better have a name for the limit. So there exists a Z in E with norm Zn minus Z2 tends to 0 as n tends to infinity. That's what norm 2 convergence means. And since norm Zn2 is 1 for all n, it follows that norm Z2 is also 1. A standard exercise if you haven't ever checked it. But in particular, Z is not 0, which is what we really want. Don't forget, though, that Yn tends to 0 with respect to norm, so this subsequence Zn is also tending to 0 with respect to norm. Note, however, that norm of Zn without the 2, don't let me lose my 2, the 2 norm of Z is what I've shown to be 1. So it's a 2 norm of Z that was 1. But the ordinary norms, without the 2, of the Zn, we know are tending to 0. But now something interesting happens. This is where we use the thing we already have in an unexpected way. You see, Zn minus Z is small using norm 2. But the ordinary norm without the 2 is bounded by constant times that. But just norm of Zn minus Z2 is less equal to that constant we had earlier, the norm without the 2, is less equal to the constant times the norm with the 2, which is tending to 0, from which you conclude that Zn also tends to Z with respect to norm. Because the norm of Zn minus Z is less equal to this constant times a sequence tending to 0. So what's our problem? Zn is tending to 0, and Zn is tending to Z, but Z is not 0, both with respect to norm. So this is impossible. This violates, this contradicts the uniqueness of limits that you would have from the ordinary norm. So that contradiction shows the constant C2 does exist, and the proof is finished. Any comments, questions, queries about that proof? What did we do? We used the constant giving us an estimate in one direction to prove there must exist a constant giving us an estimate in the other direction. And I find that sort of thing very surprising. But of course, we did use a bit more than that. You don't expect for that to always work in any old norm space. In fact, you take any old norm space, if you take some random norm space and you have some constant giving you an estimate in one direction, you won't get a constant giving you an estimate in the other direction for free, in general. So we did use something else special, some of the really nice properties of that special norm, norm 2, to get us going. However, we will come later, when we deal with Banach spaces, we'll show that if you do have two complete norms on the same vector space, and one is left with a constant times the other, you do get a constant for free the other way around again. So something of this remains true in infinite dimensions. If you do find you've got two different complete norms on the same vector space, and one of them is left with a constant times the other, you do get a constant in the other direction for free. No questions? Okay, let's just discuss then some of the consequences of that. We already discussed corollary 3.9, that then finite dimensional subspaces and norm spaces are automatically closed. So we already discussed how corollary 3.9 follows. That every finite dimensional subspace of a norm space is automatically closed. Because you restrict the norm and it becomes a finite dimensional norm space. That finite dimensional norm space must be complete. Complete subset of a metric space is always closed, and that's it. Okay? Wonderful stuff. So now we'll prove Theorem 3.10, which is that no Banach space can have countably infinite dimension. But in order to do that, we need to discuss a preliminary fact. So that's no Banach space can have countably infinite dimension. Regarded as that's when you take a Hamel basis, a proper maximal linearly independent subset, which then spans the space using finite linear combinations. So if you haven't checked up about Hamel bases yet, you will want to. We need a preliminary result, which is the rather nice fact about normed spaces, that a linear subspace of a normed space, if it has non-empty interior, must be equal to the whole normed space. So here's a preliminary fact. Let E be a normed space, and let F be a linear subspace of E. Then F equals E if and only if the interior, I'll write int E of F, is non-empty. that int sub e just means, I'm just reminding you that I'm taking the interior u in the norm space E. And this is an easy exercise, for which I'll give you a hint. Because F is translation invariant and closed under scaling. Translation invariant by elements of F, of course. Using elements of F. And also closed under scaling by real constants is all you need. Closed under scaling doesn't mean closed. What do I mean? It means that, so if I find a little open set somewhere inside F, I can translate it using a point, using a vector in F or whatever. I can pull that neighborhood bound and get a neighborhood of the origin. Then I can start scaling that neighborhood of the origin up and up and up, and I quite quickly see that every point of E ends up inside F. So you suppose you've got an open subset of E that's inside F. It's an open neighborhood of some point. You pull it back to the origin, and you find an open neighborhood of E round the origin that's still a subset of F. Then you start scaling it up by big multiples, and you're still inside F, and you quite quickly see that every point of E is inside F. So that's how it works. But I'll leave you to check details. And that's what we'll use. So we're going to use the closed sets version of the Bayer category theorem to prove our result about countably infinite spaces. So let E be a countably infinite dimensional vector space over F. F being R or C. And let's take a Hamel basis for it. So let V1, V2, V3 be a Hamel basis for E. So that's a sequential Hamel basis. You need all of them, but there's only a countable sequence of them. So what's happening here? Every element of E is some finite linear combination of some of these things in this Hamel basis. Not an infinite sum of them, but some finite linear combination of them. That's what a Hamel basis gives you. Now, suppose for contradiction that we can put a complete norm on E. So suppose it can be given some complete norm. Now I'm going to use some finite dimensional subspaces that expand out and give you the whole of E to get a contradiction. Set En to be the linear span of the first n vectors in the Hamel basis. So that's the linear span. So this is for each natural number n, we take the linear span of the first few. Then, of course, E1 is a subset of E2, is a subset of whatever. And each En is a finite dimensional subspace finite dimensional linear subspace of E. What can you tell me about finite dimensional linear subspaces of norm spaces? Sorry? Yes? Closed, yes, that's right. Thus, each En is closed. Also, E is a union of all of them. Remember, every element of E is a finite linear combination of some of the V's, which means it's going to be in one of these subspaces, because this subspaces include every possible finite linear combination of the V's. You tell me which finite linear combination you want, and which V's are involved in it, and I'll tell you how far you have to go before your element is in one of these. Well, at least I'll tell you how far when you're safe to go a certain distance. Anyway, so E is a union of these closed subsets. So it's a union of a sequence of closed subsets. E we've assumed to be complete metric space. What does Bayer category theorem tell us? This is the union of closed sets version of Bayer category theorem, which is quite a useful version of it. So by the Bayer category theorem, Bayer category theorem tells us one of several versions we did, and it's the most useful one in this module. It comes up again and again. That if a complete metric space is a union of a sequence of closed sets, then at least one of them has non-empty interior. By Bayer category theorem, there exists a natural number n such that the interior, work in E, of course, of En is non-empty. Yes?
Is this a similar thing to what we're meant to do for question 7 on the function?
It is similar to the type of Bayer category theorem you should use there, yes. Yeah. No, the union of a sequence of closed sets is a very useful one. And we're going to see it again and again. So do go back and look at the various different versions of the Bayer category theorem we gave. It's one of the corollaries to the Bayer category theorem, but this is the corollary that's most often used. Okay, so at least one of these linear subspaces has got non-empty interior. What did I say about that? What happens if you've got a linear subspace of a norm space and it's got non-empty interior? Sorry? It must be equal to the whole space. Well, so that points to the fact we could have had an alternative proof structure. I did this by contradiction. The contradiction here is that shows that E is finite dimensional, but I assumed it was accountably infinite dimensional. The alternative proof structure is I could have... I think perhaps you have to do it this way, actually. So this contradicts the fact that E is supposed to be infinite dimensional. I wonder if there's a non-contradiction way of doing that. I know what you could do. It's a bit artificial, but if you said you had a Banach space which was at most countably infinite dimensional, then you would say there would be a sequence which spanned, and then you could do this and deduce that it was finite dimensional. But perhaps that's more artificial. I think this is probably better. So that's a contradiction, and the conclusion then is that there's no such complete norm. There are plenty of countably infinite dimensional vector spaces around, like the polynomials in one complex variable, a nice countably infinite dimensional complex vector space. This shows that there is no complete norm you can put on that vector space, which answers one of the exercises I set earlier. And we better stop there.